Welcome back. This is an Aleks training video on using general properties of reaction enthalpy. This looks seriously hard, and it's not. I think you'll get it. First of all, you have to know what enthalpy is. Remember, enthalpy is that energy, all the heat in the system at the beginning and the end. So there's energy in the bonds inside the reactants. And when the reactants break apart in order to make the products, that energy is released. Then the products require energy to put together the Legos of the product. And so some of that energy is used, or all that energy is used. So energy from the reactants, if there's more energy in the reactants than the products, the energy is released into the environment. That's called exothermic, and it'll get hot. Or if there's not enough energy in the bonds of the reactants to form the bonds of the products, energy will actually be sucked out of the environment, and the air or the region around that chemical reaction will get cold. So it'd be like a cold pack in a first aid kit. All right. So if you remember previous lesson, if your delta H, if your enthalpy is negative, it's an exothermic reaction. If it's positive, it's an endothermic reaction. So if it's positive, there's more energy at the end than the beginning. If it's negative, there's more energy at the beginning than at the end. All right. So in the case of negative 559 kilojoules of energy, you're going to have, this is an exothermic reaction. Now, the easy part, because this looks awful. You've got a formula, okay? It's balanced. Okay, you've got a balanced equation. You've got some information telling you that there was energy dumped out. There was more energy stored in the bonds here than stored in the bonds here, and it was this much energy that was released. If you look at this reaction, now you have to be careful. Compare the two each time. This one is simply going backwards. This is your first guy. Here's your second guy. That's products up here, but reactants here. Here's your first guy here. Here's your second guy here. They're exactly the same. All of the coefficients are the same. That means it's just going in the reverse direction. Well, if this one is releasing 559 kilojoules of energy, then this one must be absorbing 559 joules of energy. So it's just going to be the same number, but it's going to be positive. This will be 559 kilojoules. So if you have a reaction that's going backwards, it's just going to be the other sign. It'll be the same number, but the different sign. If it's negative going forward, it'll be positive going back. All right? So look at this second one. The second one is not backwards. It's forwards, but everything is divided by 2. I've got this divided by 2, that's half. I've got 4 going to 2, that's 2. I've got 1 going divided by 2. I've got 2 divided by 2. So everything is divided by 2. So it's going in the right direction, so it's going to be negative. But it's not going to be 559 because only half of it was used. So therefore, it's not going to dump that much energy. It's going to dump half as much. If half as much material reacts, half as much energy is going to be dumped out. So what's half of 559? 280. So this will be negative 280 kilojoules. Okay. Now what's going on in the third one? All right, it's reversed again. It's just like the first one, it's reversed, so it's going to be positive. What's happening to the numbers? This is 1, this is 3, this is, this is 1, this is 3, this is 2, this is 6. So everything's being multiplied by 3. So I need it to be positive. And I need this 559 tripled, which is 1677 kilojoules. So all you're doing is manipulating the fact that you know how much energy is being dumped out or absorbed, and then as you modify the formula, either going backwards or forwards, you can simply modify the enthalpy. Okay, so it looks scary, but it's not that bad.